Hello there. My name is Jose Ramirez and I work for KPN BV as a DevOps engineer. I'm happy to be here to share my experiences at Cloud Native Data Management Day. Currently, we host our own on-premise container platform, Kubernetes based, and we offer services oriented to development teams. The platform is called KMCS, which stands for KPN Managed Container Services. Today, it is my pleasure to share my experiences with persistent storage in this platform. But first, a little bit of info on who we are. KPN is a leading provider of telecommunications and IT, a market leader in the Netherlands. We serve customers at home and abroad with our fixed and mobile network for telephony, data, and television. KPN focuses on both private customers and business customers, from small to large. In case you were wondering, this is a picture of our headquarters in Rotterdam. Now, for today, I'm planning to talk with you about the road that got us to build our own Kubernetes platform, how we set our minds to it, and what premises guided the process. I will discuss with you the idea of KMCS and how we handled the very complex issue of persistent storage with containers. Let's start with a quick look to the past. In the good old days of before 2014, when Kubernetes was open source released, most applications were comprised of code, configuration, and resource files and databases bundled together in one single node. This node could be virtual or physical. It was fairly common that in order to get an application published, several teams needed to work together. ES teams, developers, networking teams, security, configuration management, backups, etc. Provisioning a VM could take days, and publishing an application in on-premise infrastructure was not an easy task. Developers often complain about a lack of agility, how hard it was to scale, and how often they encountered downtimes due to changes in the load or single points of failure. Other issues, such as lack of portability and control over the infrastructure, were key points that affected developers then and most of the time still do. Nowadays, most companies aspire to a microservice-oriented architecture in a modern environment. Kubernetes has become a reality for years now in the application delivery landscape. In a world where time to market is essential, more and more applications are delivered as containers with Kubernetes in the center of it. So in this scenario, the question that rises is, how does this affect large corporations? So as it turns out, application modernization has become a challenge for large corporations with a high number of legacy applications. This type of corporation usually struggle in their journey towards microservice architecture. In our time working with customers, we realize there is not one single way to migrate towards microservice architecture. Each team has its own goals and a different maturity in their DevOps practices, and that makes the whole process complex for large organizations. When aiming at providing a platform that can accommodate all sorts of customers, regardless of where they are in their journey towards cloud native architecture, we found different needs tend to coexist when it comes to persistent data. On top of all this, there is a plethora of tools available for Kubernetes environments that make it even harder to select the right tools for the job. We can see a screenshot of the CNCF landscape website. This screenshot only shows a fraction of the tools available for Kubernetes. So based on this, we decided to build a platform that tackles some of these issues. But first, we needed to evaluate some premises. We asked ourselves, what is a developer's dream and how we could come as close as possible to resolve it. As it turns out, most developers have a simple and yet very complicated set of aspirations. Of course, that we all agree on a certain number of them, and more or less we see that they consider that something that is easy to update and to modify. It's a plus, some environment that never goes down, that they don't ever need to hear the words OS patching, that secrets and credentials are kept magically safe, that data is always available, backed up, protected, and that the environment grows on demand. That is usually the kind of set of of requirements that we get from developers, so they can focus on the code. For them, the code is always what matters, and we can always agree on that the code is always what matters. However, we have seen that when development teams choose to run their own Kubernetes platform, they find themselves using more and more time maintaining and operating the platform that could otherwise be used on application development. Not to mention the time needed in training and skill development in the team to manage this Kubernetes platform. Everyone that has taken a look recently to the documentation of Kubernetes realizes the change in mentality needed to migrate from legacy applications to microservice architecture is huge on itself. Adding to it operating a Kubernetes platform all by yourself, and it's very easy to just feel overwhelmed. Not to mention that there are issues that are native to Kubernetes and inherent to the design of Kubernetes itself, such as the persistent problem of persistency in containers. So most teams have a portion or several portions of their application that is stateful. Development teams usually don't want to run the stateful parts of their applications away from the container runtime. On the other hand, Kubernetes was built with stateless applications in mind, but has grown to include more workloads nowadays. An extra layer is typically needed to provide the persistent storage to the container running on Kubernetes. With all these ideas in mind, we set ourselves to create and build our own container platform, and we created KMCS. So the question comes like, what is KMCS? It is basically our own KPN Managed Container System. It is customer-oriented from the start and takes away all the complexity of operating Kubernetes clusters from the development teams. It can be customized to suit the particular needs of the teams that use it, and basically all the developers need to do is to code, build their images, and deploy. As simple as that. How is it different than everything else that is out there? And what can it do for you? So the services that KMCS offers are separated in logging, container security scanning, backups, NDR, data protection, among others. They all can be consumed individually or as a whole. All cluster-wide objects are managed by the KMCS team, removing management overhead from the development teams. Our team participates in the onboarding process, providing assistance when it comes to transforming legacy applications to fit in the new Kubernetes way. In view, there is a general application description of the KMCS architecture. So KMCS is comprised of several subsystems that we provide. We provide a container runtime engine based on Docker and orchestrated by Kubernetes. From the customer perspective, KMCS is accessed from CI/CD pipelines or kubeAPI clients. From there, our customers have control over their namespaces and the resources they create, without concerning themselves with what lies underneath. We use decoupled components to provide the network layer, including load balancing, web application firewall, DNS, ingress controller, among others. They are used by our customers using annotations in their deployments. As a part of KMCS, we provide our own container registries that serve as a source for all the images running in the container platform. Container security has been a hot topic in industry for quite some time now. And in order to satisfy the security needs of our platform, we provide to our customer a platform security component that is in charge of all the aspects of KMCS security, such as scanning images on push to the registries, and in runtime scanning as well in the platform, as well as CIS benchmarks. As a storage layer, we use Portworx that provides a container-oriented storage that is consumed by our customers in the form of standard PVCs. So when we decided to build our own Kubernetes platform for our customers, it became obvious that Kubernetes on itself had several areas that needed enhancements. A stateful storage layer was needed, obviously, to accommodate workloads such as databases. When selecting this layer, we found several requisites that we needed to get covered to basically get it right. And that's another thing we found out. Like, storage is one of the areas in any IT system that we want to get right, and ideally we want to get it right from the very beginning. Migrating or changing storage systems in production is always a very stressful job, and we identified the following areas that really need to be covered before we even started. Number one is the scalability. We wanted something that could grow as we grow. A backup solution that we can use to take snapshots or to back up all the information from our customer to a safe place. It needed to integrate very well with our pre-existing monitoring and logging tools. We needed an RBAC solution that was capable of providing multi-tenancy of this storage layer. We needed it to be secure, and we needed mechanisms to ensure disaster recovery was available for us when needed. So after careful consideration, we decided to use Portworx since it checked all the boxes that we needed to satisfy in the original design. That's how we started with it. Portworx is the container-oriented persistent storage layer that we use in KMCS. Customers use it by creating PVCs from a set of storage classes that are predefined by the KMCS team. These storage classes are created based on the I/O patterns they are optimized to serve, so customers are encouraged to select them based on their I/O needs. These storage classes already contain a replica number defined by us that is based on how critical this service is. For instance, a database storage class has a replica 3 by default that creates 3 replicas of a persistent volume. In order to solve all the different issues that we found, number one of them was scalability, and here in particular Portworx excels. So we needed a platform to grow alongside our customer base. So Portworx is installed as an even set in our clusters. Because Portworx is using KMCS as a hyper-converged solution, every new node that is added to the Kubernetes cluster is automatically added to the Portworx cluster. In KMCS case, our nodes are prepared in advance via Ansible before they are joined to the cluster. Once joined, Portworx daemon set makes sure that the node is provisioned and joined to the Portworx cluster. If we add new drives to a pre-existing node, the storage is not available to Portworx automatically. A drive addition process is needed to get that covered, so that's one of the things that we learned along the way. As a standard way of creating backups, Portworx offers a PX backup, which is a great solution. But by the time that we started with Portworx, PX backup was not yet released. So we used our own solution to provide backups using a backup cron pod. That is basically a piece of software that creates cloud snapshot of volumes based on the group they belong to, and this group is predefined by the storage class and uploads it to the KPN S3 storage. It also backs up all the latest versions of the KVDB snapshots, which is the key value database of Portworx that you certainly want to keep a backup of. All these backups are taken automatically every day, and they are uploaded to the S3 storage, as I was saying. As an extra precaution, all customer volumes are created with a sticky label. So even if they are deleted by the customer, the volumes are kept in Portworx. We have a garbage collector job that cleans any sort of unused data, unused persistent volumes left detached for longer than a month in our infrastructure. On top of that, users can create their own backups using Kubernetes objects such as volume snapshots, application backups, or group volume snapshots. In KMCS, we needed an RBAC mechanism that allows us to have our customers authenticated at the storage level. Portworx provides an RBAC method using JSON Web Tokens that allows each namespace to have its own token for authentication purposes, with volume, ownership, and privileges assigned based on it. Portworx supports also encryption of data at rest. It's not enabled by default, but in KMCS we enable it by using our own key in all the storage classes. Customers can and are encouraged to override our key at a PVC level by just declaring their own key. So when it comes to disaster recovery, from the very beginning in KMCS, we plan to use asynchronous DR with Portworx, replicating applications and their data between two Kubernetes clusters. A separate Portworx cluster runs underneath each one of these two Kubernetes clusters. The active Kubernetes cluster syncs apps, configuration, and data to the standby Kubernetes cluster. This is done in an asynchronous manner. And this standby cluster basically ends up running controllers, configuration, and PVCs that map to the local volumes that are in the other cluster. Any incremental changes in one of the clusters, it's transmitted to the second cluster asynchronously. Although we're not using it in KMCS at the time, Portworx also supports a synchronous DR when installed as one single cluster stretched across multiple Kubernetes clusters. There are several restrictions to it, like you need a latency between these two clusters to be lower than 10 milliseconds. Otherwise, the synchronous DR won't work. When it comes to monitoring and logging, we needed to integrate with Sysdig for monitoring and with Promptail, Loki, and Grafana for logging. Portworx supports compatibility with all the elements mentioned in this slide. And as you can imagine, if you know anything about Loki and Grafana, providing multi-tenancy with these two tools require a lot of in-house development. And we're happy to say that we achieved it and we got it in production. In our time operating Portworx, we found several interesting things that I would like to share with you. One of the most dreaded parts of operations is typically upgrades. With Portworx, upgrades are very simple. Basically, we take a script that is delivered by Portworx with each new release. We run it, and it triggers a job inside the Kubernetes cluster that performs an upgrade of Portworx in the running release manner. That way, you only have one pod down at any given time, and it's not even down, it's just has the persistent volumes locked in read-only state. So that's one thing to keep in mind. The other one is that every single time we need to conduct a disruptive operation for the node, we always place it in maintenance node from the Portworx side to prevent data corruption. This is a good practice that is encouraged by Portworx as well. And so far we have been using it. We haven't had any issues. And the bright side is that until today, on all the time we have been operating our platform, I can say that Portworx just works. We at this point we didn't have a major issue that was caused by Portworx per se so far. So it's great. I would like to close by mentioning a small look into the future and the current implementations that we are working on. This is one of the latest things that we're working. We're planning to use Prometheus metrics exported by Portworx to inject them into the autopilot component of Portworx. This way we can achieve automatic resizing of PVCs when they are getting full and scaling the storage of our customers' applications on demand. It's a very interesting feature that we cannot wait to see what our customers do with it. To close, I would like to thank you for your time. I hope that you learned something today, and thank you for watching.